This is the Properties of Fog by Group 28. So to start off this, we went and saw a video on the San Francisco fog. It's a 4K timeline. Now here specifically, we can see the fog rolling in slowly over the mountains, and as the temperatures and pressures of the localized area change, we are able to see that the fog is slowly able to move in more easily and encompass more of the city. This is not only due to the temperature and pressure change, but as well the saturation and dew point temperature of the local area changes as well, as we will see later in the presentation. We can see throughout the day as it slowly starts to heat up that more and more fog is able to cover more of the area, which is a quite interesting phenomenon. And we wanted to look into the different properties of fog and how they are affected by things such as pressure, temperature, the local geographical area, as well as the difference in the saturation of the soil and different topographical features as well. So as we can see here again, as the day moves on, we see more and more fog rolling into the local area in this little time lapse here. And we will see more about how and why this occurs in the quantitative part of our analysis of the presentation. So going in here, we can start the presentation. So our hypothesis that the fog and the formation, flow, and dissipation of it has key factors such as differential pressure and temperature of the nearby area, nearby bodies of water, the typography, and the wind conditions of the area. So to go into our analysis, the first key point that we noticed is we wanted to see how the pressure change affected our fog. So here we can see we have P1 and P2, and P1 is greater than P2. And with our Bernoulli equation, we set it so that we have the set up Bernoulli equation. We assume that height and density does not change with this sample set of fog. And we can see here that due to the pressure change, the fog will flow towards the lower pressure location at a higher velocity, which intuitively does make sense as things tend to move towards a lower pressure zone. They'll always go towards the path of least resistance. And these fog formation conditions are determined by the dew point temperature. This is a simplified dew point temperature calc, as we can see in the lower left-hand corner. The temperature dew point is determined by the ambient temperature, and then it is 100 minus the relative humidity divided by 5. And this gives us a simplified calculation of the dew point temperature. And whenever the ambient temperature is equal to our dew point temperature, we will start to see fog formation throughout the region. Now you can see in the top right hand of our presentation, we have the different fogs, and we have the less dense fog, and then we have the more dense fog. And we wanted to see how the density of the fog would affect the velocity. So we set up our Bernoulli. We set the pressure plus 1/2 rho times v squared plus rho gh is equal to our constant. We assume that height and pressure does not change in this scenario, only the density of the clouds. We can see we have 1/2 rho is equal to our constant divided by v squared. So from this, we can clearly see that when the equation is solved, our density is increased, and when our density is increased, the velocity denominator must decrease in order for that term to stay constant and for 1/2 rho to be equal to the constant over v squared. Now we have two different types of fog. We have radiation and we have ambient fog. Radiation fog occurs where the temperature is cool, we have saturated soil and clear skies. This would be fog that you would normally see early morning whenever it's on a quite hot day after a long night of rain from the previous night. So you'd see an increase in temperature, and you'd see that even though the air around you may appear to be cooler, it will slowly start to warm up. So on an early morning walk to school, you definitely start to see some fog formation. And then we have ambient fog, which is warm, saturated air moving in towards a location of cooler and less saturated air. This occurs where it creates a pressure differential. This would be what we saw in the video of the San Francisco Bridge, where the fog slowly starts to move in and move from a warmer from the warm saturated air moving into the cooler San Francisco Bay air, which creates those large amounts of fog. So our conclusions from this is that fog will always move from a lower pressure area, will always move towards the lower pressure areas from a higher pressure area within a given space. This is why it is unusual for fog to be so low to the ground generally, as more often than not, the higher you go up in the atmosphere, the lower the pressure is. So it was quite fascinating to see conditions where fog gets lower and lower to the ground. And then fog that is denser will move more slowly and it will take longer for it to clear out and have lower velocity, meaning road conditions will be dangerous longer, which is something that we don't often think about. But when thinking about how long it takes for road conditions, the more intense the fog, the longer it will take for that fog to clear out and for people to get on the roads and be safe. On this slide, we can see the references that were used for this presentation and all of the data that was pulled there and different equations that we had used. Thank you. This has been Group 28 on the properties of fog.